Hello everyone, it's really my great pleasure to be here today and have a chance to talk about our work on vision and AI during this summer school. First of all, I would like to explain where are these vision and computer vision and AI actually used in broadcasting scenarios. Why is this important for a broadcaster? Well, broadcasting media industry hugely depends on engineering innovations, on new ways to deliver content, make content interesting to people, and therefore all this work from research communities on AI sooner or later has some impact in some form to the broadcasting industry. So basically, yes, maybe the examples of our research that I will use today do not apply immediately to your research. I see you are coming from different application areas, but still there is a lot to be reused, I believe, in terms of very fundamental algorithmic ideas that can be applied to various different areas. So just to put our work in some context, here we have this very simplified graph of, at the beginning, lots of content. This content can be lots of old video clips from archives, lots of video clips from social media, lots of video clips contributed by audiences to BBC during some event. So what is really desirable to have is more automatic check of videos, check of pixels, check of content, and also quality. We cannot put any video back to the programs. So the idea would be to apply, let's say, tailored enhancements and tailored analysis algorithms based on where the content is coming from. I'll show examples later. Once we have all those enhanced videos, producers who want to produce, focused content for that lasts limited amount of time have problems selecting which clips to look at. If you have thousands of videos, where to start from? That's why we need a way that automatically somehow clusters video or recommends videos based on various properties, and it is this block here. Once a program is done, it can be used on all different services a broadcaster have. In this example, it's all BBC, but of course, this is here just to demonstrate that, content for the website, content for satellite, content for my player, and so on, can be the end for this chain where vision algorithms are used. And this is basically what we work on in my team in BBC R&D. What is common to all these steps is video compression, and video compression is topic that I spend most of my time on, and therefore I'll start with it. Why video coding? So there is no one-to-one map of AI, machine learning, deep learning to video coding, but there is a very, very big overlap. And about 15 years ago, the first standard that enabled streaming on mass scale, that means reduction of video to a bandwidth that was small enough to be distributed on mass scale, That standard was H.264 AVC. We used some machine learning already then to design algorithms on how to squeeze the bits. So these three different sets of wires represent how much bandwidth you need to send some bits of a video. 15 years ago, more than 15 years ago, when this standard was designed, computational power was limited, and we didn't think much about 4K UHD videos. It was difficult to find HD videos in those times. A lot changed in other disciplines. So basically, in 10 years before the standardization of H.265 HEVC, there were many advances that enabled us to squeeze the same amount of bits even more to deliver the same video quality. And this is what we, as part of much bigger standardization communities, did, well, already more than 5 years ago. What was enabled by that? Yes, this line says we were able to send UHD and HDR videos on mass scale, distribute them to millions of people. But more importantly, this new standard had the capability to reduce costs, reduce delivery costs, and make even more people on lower bandwidths able to watch streamed video. So this was happening also partially because of computer vision, machine learning advances. Finally, at the moment, a new video coding standard is being developed. That is VVC. Soon you will hear about it. The aim is to again enable compression of visual informations of video even more, to halve the requirements of HEVC, and in a year or so have a new standard. So basically, so far, video coding used this simple, let's say, version of AI, some statistics, some logical operations, and so on, and machine learning. But the advances in deep learning, which I'll address later, open some new possibilities. We'll see that later. So this is just basic history of video compression, so that we can then address specific topics of enhancement of video compression. So basically, video coding algorithms, in addition to some statistics and some machine learning, a little bit of it, are mainly based on signal processing and also taking into account perception science. And this is usual diagram of a video codec. We have input video signal, and here we have coded bit stream. In the meantime, what happens is compression. We are compressing, I don't know, 100 times, 50 times, depending on application and many other factors, requirements for transmission. In addition to all these nice algorithms, nice, let's say, tools that we can use to perform good compression, we also need a lot of brute force. That means in order to optimally squeeze bits to reduce bandwidth, a lot of computation is needed. And every new standard is more and more complex. On this example, basically it's shown that we compress a frame by splitting it into blocks, and then maybe we split blocks further. Why? Because if, for example, this is a big black box, block, why spend lots of bits to describe each pixel, each of 1,000 pixels within it. If we can, in a more simple way, say, this is a big black block. No? But if we have more details within a block, then we want to split it into more distinctive areas, which can then be compressed better. And this typically optimal solution is, of course, try all splitting options and see what is better. But that takes time, and you don't want to invest too much computational power, or you have basically requirements to do the compression quicker. That's why some of our research involved how with machine learning we can basically reduce the complexity of video encoder trying to find the optimal splitting of a frame. And typically, like in many other tasks, you need some hypothesis, and in this case, our hypothesis was that we could reduce the cost of splitting by looking at some properties of those big blocks and surrounding area. So based on that, perhaps we can learn something, so that next time we don't go into all the split options of a block when we want to compress it. There's this small picture here on the right hand side shows, out of many options, we basically want to eliminate options. We want to learn options that are not worth checking, and then just leave some that are worth checking and reduce the complexity by doing so. So obvious option would be using support vector machines, extract some features. In our case, for each block we extract, I believe, 7 features related to the current block and surrounding blocks. So in that 7-dimensional space, have mapping to this hyperplane and trying to figure out which one would be optimal cut to decide whether to further split that block or not. And we got some good results. We found a way to, reduce the number of splits per block we have to do. This diagram here shows in blue like original time needed, and then in green new time needed to compress a video sequence with our HEVC Turing codec. At least some savings we got here, but this is just part of the story, because actually in order to run SVM on so many blocks we need some time, and this is complex. And in the worst cases for this Nebuta sequence, when anyway the reduction of core compression time got smaller, we actually overall increased processing time because SVM was just taking too much time. Basically, this shows that some research results depend very much on the framework that you use, and even very efficient machine learning algorithms are not always good for application, for practical application. So what we did is look for less complex approach. Natural option was to use decision trees. So we didn't go to more complex things like, I don't know, CNNs, training of deep networks and so on. That would just make things more complicated. Let's see what we can do with simple approaches. So basically we again took those 7 parameters for each block, and then we tried to, for each of the feature, say what is more likely for a block to be splitted or not. Made a tree which basically best describes how these 7 features can be correlated with whether to split block or not. And we got some interesting results, as this diagram shows. Quite good saving in processing time, approximately 40% saving for very, very small quality of video loss. These are quite good results. At ICAP we are not the only one this year who will present similar algorithm. So if you are attending ICAP, you will see more there, and also our paper is available online. It is this first paper from Natasha. Her work also inspired, so Natasha works in BBC R&D. She was working on this project with me at the same time with when Ellie, here from Queen Mary, was an intern with us. And Ellie was working on AV1. She's a PhD student here and did a couple of months with us at BBC in West London. So what Ellie did was to apply the same algorithm Natasha built to grow this optimal decision tree, but for application in AV1 video coding standard. And she got also quite good results, which are very similar. They use totally different set of parameters for each block, but she managed to save roughly the same amount of time for this search and so on. She published that at ICASP earlier this year. So this video should slightly demystify how these trees grow. We first have to grow trees and then clip some of the branches. Basically, out of all features, we first select the one that best splits the data into different classes, like split and non-split class. And that's what we put into the root of the tree. So once we know the property of that one parameter and its influence on whether to split tree or not, we try to figure out what is the next best parameter to split the new nodes of that tree. And we can continue until we reach the optimal tree structure. And then once we have such optimized tree structure, we implement it with simple if and so operations in the recursive algorithm on quad trees within video codec that splits the tree. So basically, having something like that with almost no computations in the hard-coded can provide quite good results on a wide range of video content. So basically, this shows that sometimes low complexity options, easy options are good. And what we like about this approach is that we absolutely know what the algorithm is doing. We know what each parameter means, and we know what is the value which will trigger some decision. It's not always like that in machine learning, especially not in deep learning. So, but there are other fantastic things that we can do with it, and that's why I'll continue now the talk with some examples of our work related to deep learning. So what is different between deep learning and what we were doing so far is, as most of you know, that the idea basically comes from brain research, where now understanding is that group of neurons during our lifespan form connections, especially in our early days, to basically how are they connected to the next neurons and so on. So group of neurons sort of pass the information to each other, and this can be because of computer power and lots of data now used for in computer science to learn various data properties. It is not immediately clear maybe here what we can do with visual data in this case, but luckily we have convolutions, good old convolutions that help us somehow provide more meaningful input to the deep network than just putting all the pixels from an image. And here is an example now which shows basically if you train one network, what are actually the features that computers see during application of this trained model, for trained model. Basically, there is nothing, let's say, too intelligent about it. It's something learned from the input data, how to interpret input video. But what is interesting is what we can do with it, right? Especially in terms of television and media streaming scenarios. Believe it or not, we can use it for video coding as well. So one of our PhD students, who is also here at Queen Mary, but typically sits at BBC, Maria Santa Maria, used CNNs to develop one network, shown here, which in this video coding graph basically can supervise the whole coding by estimation of quality and bitrate for a given frame. That means, depending on the content, her algorithm can estimate what would be the pair quality and bitrate, and this can then optimize the rest of video coder. This was published at VCAP last year. She's now looking also how to use CNNs in interprediction. Interprediction means that basically, if you have to predict one block, because surrounding pixels are similar in some way, maybe we can predict them from surrounding pixels. There are ways to do that 20 years old, but with CNNs it looks like we have actually with deep learning, not necessarily CNNs, we have ways to better predict what is in each block, which is very important for reduction of bandwidth of the video we send. We are also using CNNs and deep learning for color prediction during compression, and experimenting with using convolutional neural networks for interprediction. Interprediction is basically, because the frames are very similar, next frame can be predicted from previous frames, right? In 1 second you typically, let's say, have 50 frames, so using CNNs you can refine the prediction. In this video basically we just show some motion vectors related to that research, but at this point we can basically conclude that machine learning can be very efficient in video compression if we use it very, very carefully. So we cannot just blindly apply algorithms without understanding deeply all the parameters and things that are inside video codec, all the signal processing that is around it. We observed that efficiency can be improved, video coding efficiency, like better prediction, accuracy. We can make better decisions, better predictions, cost reductions, and also quality improvements. So this is one active field of research, and many results are emerging. All this knowledge we also reused in various collaborative projects on different vision problems. Here you can see one video where basically a video on the left-hand side is enhanced using CNNs to get this video here. You can see the bars at the top, probably that they are much sharper, the visibility is much better. I'll try to show you some other examples as well. For example, letters here. You can see how much better they are. So this is quite important for making the video that is going to be broadcasted better. Actually, this particular implementation was done in a collaborative project with QMUL. It's quite good. Then this is another example of using deep learning, this time in helping producers to make stories. In databases with many videos, in this case user-generated videos, it's sometimes difficult to find similar videos. And in this case, by labeling current video with some with interpretations of extracted features, one can search thousands of other videos in database quickly and produce similar results, which can then be used in production, put into programming that are of better quality or slightly better image quality and so on. This is also quite powerful use of machine learning. And some of our recent results are shown here. Let me see if it plays or not. So what we do here, we have black and white images, grayscale images, and we want to colorize them. We want to add color. So this video shows the training process first. So depending when we are in the training process, of course, the prediction of color for these images is different. And then at the end of the process, we can use trained network to get quite good predictions. We here also display some ground truth results, which are not always. Prediction is not always perfect, especially if you look at the beer. Our algorithm gave us transparent beer, not yellow beer, so colorization went wrong. What is good about this, special about this work is that basically it made a big change in terms of colorfulness. Because during training you can very easily end up with a model that makes all pictures very brownish or maybe blue. I remember sea and sky examples from many trained models that basically cannot be applicable to a wide range of images. So we did a specific careful design of GAN to enable more natural prediction. Okay, so finally, just to conclude what we covered in this talk, some promising applications of machine learning, and in particular deep learning, will enable automatization of many traditional, very complex tasks such as colorization or adding details to video. This is a breakthrough, and we are very interested to see more being done on this topic. In video coding, which is the technology that we use, all of us, all the time, every time we watch some video, machine learning can still provide some additional reductions of bitrate and bandwidth, which are important in helping you have better experiences of watching your video content, squeeze more data of high quality content to deliver better content to you. Overall, a lot is happening at the moment, and this is thanks to these new algorithms coming from machine learning. And finally, this is our team from BBC, people who actually did the work, at least most of them. You will also recognize some faces here, as some of them are regular students here or are coming from Queen Mary. And that's all.
Thank you.